This is just a heads up to let you know that this video is about double the length of a normal video. Well, today we'll study the craze that's sweeping the nation. Triangles. They're everywhere. But before you can get into serious triangle spotting, like everything else, we have to be able to categorize them. Let's start over here. What do we call this? Scalene. Why scalene? I'm not sure. In Greek, it roughly means something like unequal legs or something like that. Scalene means that none of the sides are congruent. They're all different. That's why I drew the hash marks the way I did, to indicate that they're all different. You don't really know what they are, but none of these are equal to the other. Next, we have isosceles. And iso. That means equal in Greek. And celes, well, that's similar to a Greek word that means leg, or legs. Equal legs. That's what it means. Iso, you'll see that in front of lots of things. It means equal. And this one isn't equal to those two. Remember, the little hash marks tell us that these two legs are equal. We don't know what they are. We just know that. And I really should say congruent. Their lengths are equal. The two sides are congruent. And over here, we have equilateral. I think slats mean something like sides. Not really sure why they don't say isolateral. Could be a different root. I don't know much about that word because it sounds so much like what it means, equilateral. These hash marks are intended to imply that each one of these sides is equal. So what we did here, we classified each of these three triangles according to the lengths of their sides, not the actual length, but the relative length, in the sense that no two sides here are congruent, here two sides are congruent, here all three are congruent. And that's about the only three possibilities you've got, right? So that's those three. What about down here? Well, you're going to see some similarity, some redundancy. This is called an acute triangle. Why? Because every angle here is acute. They're not congruent, but every single angle is less than 90 degrees. Remember? This is all stuff we studied back years and years ago when the course started. Acute means less than 90 degrees. Obtuse, which we're going to get to in a second, means greater than 90 degrees. And we've been using right triangles right along, right angles right along, so you won't have any trouble remembering what the right angle means. So this one here is an acute triangle because all the angles are acute angles. This one would be a right triangle. Why? Because it has a right angle. This is an obtuse triangle. These are going to be kind of easy to remember because if you can remember acute angle and obtuse angle, the triangles that have similar properties take exactly the same names. We have an obtuse angle here, greater than 90 degrees. And this is called equiangular. Yeah, when's the last time you heard anybody use that word? I bet it was a long time ago. When's the last time somebody knew how to spell this word? Equiangular. There we go. And that means, well, you probably know exactly what it means. Each of these angles is congruent. All three angles are congruent. This triangle looks like it has properties similar to this one. Well, that's not a coincidence. We'll show later that there's a definite relationship in there. So, if we're going to go out triangle spotting, these are our three main categories. You got your scalene, isosceles, and equilateral. These are all defined according to the sides. And acute, right, obtuse, and equiangular. These are defined according to the angles. Can you have both? Yeah, of course. This is an isosceles triangle. It's also an acute triangle. This is obtuse. I think you could also say it was scalene, so I didn't draw any of these sides to be equal. So there is overlap. And here we have the theorem that this section is all about. Notice it's titled Triangle Sum Properties. And here we have the triangle sum theorem. What a coincidence. And this theorem says, it's not a postulate, it's a theorem. And we're going to prove it. Just in case you don't think it's true, I'll show you that it really is. And what it says is that each of these angles, when you add them all together, they add up to 180. And of course, I should say the measure of angle A plus the measure of angle B plus the measure of angle C equals 180, which is, oh, what a coincidence, it's written right down here, son of a gun. Now, how do you prove this? Well, you need a little trick. Remember all that stuff we did with transversals in the previous chapter? Well, there was actually a reason for that. Remember, in mathematics you tend to build from what you did before. If we hadn't studied that, we wouldn't be able to prove that the sum of these interior angles, I've relabeled these a little bit. This is small a, small b, and small c for the angle. This is small d, and this is small e. And because of what we studied with transversals, and because we made use of something that I was about to mention, which is we can add things. For instance, this line here and this line here, they're parallel. Why? Because I drew it that way. That's why. This is a line that I drew in. It wasn't there to begin with. And it's okay to do that in a proof. You can add things. Preferably you add things that actually help you complete the proof. We could run around adding all kinds of extraneous lines. I could draw a line over here and say, well, this is perpendicular. Yeah, it would be, but it wouldn't help us prove this particular theorem. So it is okay to do this. It's also okay to extend these segments. Remember, by definition, a segment is part of a line. So we can extend this out so that this is actually a line crossing these two parallel lines, or a transversal line crossing these two parallel lines. Now we can use what we learned about transversals. For instance, angle D is congruent to this larger angle here, which is covered by E and B. But it's kind of hard to write that it's congruent to E and B. We don't have a way to write that yet. But we can write angle C, B, and I added a point. That's legal. You can add points to your diagram if you want. So angle CBF is congruent to angle D. I wrote that down here. Also, angle A is congruent to angle E. We just have a different transversal over here. These are alternate interior angles. And this here, well, these were alternate interior angles also. So, what do we do now? Well, notice anything about angles C and D? These two angles? Well, they're a linear pair, so they add up to 180. So let's write that down. This is going to be an important property. Angle C, or the measure of angle C, plus the measure of angle D equals 180. But angle D is congruent to this large angle here, which is made up of E and B, and from our angle addition postulate, and from the fact that they're congruent. Remember, if they're congruent, their measures are the same. So the measure of CBF is the same as the measure of angle D, but the measure of CBF is the sum of these two from our angle addition postulate. It's kind of long-winded, but what that means is we can substitute the measure of angle D for this sum, the sum of angle E and the sum of angle B, or the measure of angle E plus the measure. Wow, I didn't even write that close to right, did I? Bad. There we go. Measure of angle B plus the measure of angle E, and over here we have the measure of angle C. Well, we've got three angles that add up to 180. We have a problem though. It's this one here. E isn't part of our triangle. If we had measure of angle C plus the measure of angle B plus the measure of angle A equaled 180, we'd be all done. But we got this E here. Oh, wait a minute. We already figured out from what we know about transversals and parallel lines, these two alternate interior angles are congruent, which I wrote down here. So I can substitute. In a strict proof, my next line should be measure of angle A equals measure of angle E, because they're congruent. Well, we all know that now, so just going to write here the measure of angle A. I can make that substitution because these two angles are congruent. Now I have the measure of angle B, and here's the measure of angle C. Now these just happen to be the interior angles of the triangle, don't they? And we've just proven that they add up to 180. And that's good because they actually do add up to 180. This is a totally valid proof. Well, it's not really a two-column proof, and as a paragraph proof I just talked most of the words and only wrote down the important stuff. And really the important part of this proof is to recognize that you can add a parallel line. And when you do that, now you've got two parallel lines cut by transversals. Now we've got a whole bunch of properties of angles of parallel lines cut by transversals that we can use. And that's exactly what we did. We just applied all the properties of angles created by parallel lines cut by transversals, and boom, with a little bit of algebra, we wound up with this really very extremely super important result. This isn't quite as important as Pythagoras' theorem, but it's up there. So don't forget that the interior angles add up to 180. That's going to be important for a long time. Here's another theorem, which, remember I told you about corollaries. Those are things that follow very easily and quickly. You could almost call this a corollary to this one because of the way we proved this. Remember? We laid this out and said that C and D form a linear pair, so they're supplementary. And that the measure of angle D is equal to the sum of the measure of angle B and E. And E is congruent to A, so we substituted. So what we really showed here was that in the process of proving this is that C and D are supplementary, but we can replace the measure of angle D with the sum of these two angles. We can use the measure of angle B because it's already part of the congruent angle CBF, and we can throw in A because it's congruent to E. So in the process of proving this, we actually proved this. That these two, the sum of the measures of these two angles, equals this exterior angle. What's an exterior angle? That's what you get when you continue one of the sides. For instance, if I continue this side here, then this is an exterior angle. If I continue it this way over here, then this is an exterior angle. Pretty simple, kind of intuitive. And the fact that the exterior angle is equal to the sum of the two opposite angles, well, like I said, we, in the process of proving this theorem, we proved this right along the way. So this is an easy one to remember. And here's one that actually is called a corollary. The acute angles of a right triangle are complementary. What they really mean is the two angles that aren't the right triangle. That aren't the right angle. Here's the right angle. And what they're really saying is the other two angles. You can say acute, but it's easy to prove that they have to be acute. Now that we know this, that they add up to 180, well, if one of them's 90, there's only 90 degrees left to split up between these two angles. So they're both going to have to be less than 90 unless one of them is 0. And that wouldn't make any sense. If this angle were 0, you'd just have a straight line. A straight line might, in some higher math classes, be considered a degenerate form of a triangle. But we're not going to consider it that way. We're just going to consider a straight line to be a straight line and leave degenerates out of the class. This is really, really simple, very obvious. If you understand that two things that add up to 90 must both be less than 90, especially if one of them can't be 0, or I should say particularly if one of them can't be 0, and you're all done. That's the cool thing about corollaries and why they're not always referred to as theorems, so that they drop out so easily from previous theorems. Just give them a slightly different name. Now here's a algebraic equation, question actually, where we're going to make use of our triangle sum theorem. And this is going to be a pretty easy problem to work out. You can draw the triangle if you want to. Don't think it really matters one way or the other. Suppose we did. Who knows what kind of a triangle it is. It doesn't say. You can draw it here if you want. It doesn't really. This is one of those cases where it's all algebra, and without the picture, you could probably figure it out just fine. We got angle F equals 3 times the measure of angle F equals 3 times the measure of angle G, and the measure of angle E equals the measure of angle F minus 30. So angle F seems to be something that we have in common with everything here. In other words, we got angle F here. So let's just start out with measure of angle F plus measure of angle G. Now let's switch things around a little bit and write that as the measure of angle F divided by 3. Why? Well, just so we get everything in terms of the same angle. Just multiply through by 1 over 3 and get measure of angle G equals measure of angle F, and then substitute. Because maybe I should have written that right up on top since we haven't done a lot of it yet. The measure of angle F plus the measure of angle G plus the measure of angle E equals 180. This is what we're working from. That's our triangle sum theorem, right up on top there. And what else? Well, the measure of angle E is the measure of angle F. minus 30 degrees. So, and that all equals 180. Now I'm going to make one little shorthand substitution. We're trying to solve from the measure of angle F, right? How about if I just write x equals the measure of angle F? It's just easier to write the x's when we go through here and start doing the algebraic manipulation. So we can rewrite this as x plus x over 3 plus x minus 30. Or, so we get 2x plus 1/3. So what we have here is 2 and 1/3 x. Add 30 to each side. Equals 210. Or, let's see, that's 7 over 3 equals 210. Multiply through by 3 over 7, and we get that x equals 9. That's what I get. Remember, we multiply through by 3/7, so 3/7 here. 3 goes into 21, 7. Wait a minute. 7 goes into 21 3 times. Times 3 is 9. Does that make any sense? Well, let's find out. Suppose we just put it here. We got 9. 9 over 3 is 3. This isn't making any sense at all. I need to keep track of my zeros here. 210 divided by 7 is 30, not 3. I was obviously looking at the 21s there, the non-zero numbers. So let's do this as if we actually knew what we were doing. Well, this is interesting. This whole thing is 90 plus 30 plus 90 minus 30. Those two cancel, and I got 90 plus 90, which is 180. So, x equal to 90 makes sense. The measure of each angle, well, angle F, it turns out, was 90 degrees. Well, is that right? Yeah, we used x as the measure of angle F. So, F over here should have been drawn as a 90-degree angle. G is 1/3 of that, so this should be a 30-degree angle. And this has to be 60 degrees. And up here, since measure of angle F is 90, minus 30 is 60. And you could also figure that out from the fact that this is a right angle. The remaining two have to add up to 60. So we've got a 30, 60, 90 triangle here. And this is all just algebra. Pretty easy. There wasn't any really big trick you needed to spot. Just lay it out the way it's written here, and then solve the equation. Okay, and here we have some of those find the error problems. Now here we have, well, some dumb guy who makes geometry videos decided that since all equilateral triangles are also isosceles, then an isosceles triangle must be equilateral. Well, come on. We know better than that, don't we? We already studied proofs, hypotheses, and conclusions, and this is what he did, was basically say, if P implies Q, then Q implies P. And we don't know that this is true. Remember, this is called the converse. Sometimes the converse is true, sometimes it isn't. And in this case, no. After all, if we were to use our old Venn diagram, say we got all the equilateral triangles here, and then the isosceles triangles here, which are contained inside the equilateral triangles. Can we go the other way? No, not everything out here is an isosceles triangle. Everything in here is. We should write this. I for isosceles and E for equilateral. Now these isosceles do fit inside the category of equilateral, but not the other way around. You could look at it with the Venn diagram, or you could just instantly spot that this is pretty much nonsense. Either way works. Now what about this over here? What did he do wrong? Oh well, he got really confused here. It's the interior angles that add up to 180. However, he was thinking maybe of something else, which is the measure of angle 1 equals the measure of these two. Remember that? That's the exterior, the measure of the exterior angle equals the sum of the measures of the two opposite interior angles. So he might have been thinking of that one, which is the measure of angle 1 equals 80 plus 50. That would be true. Or 180 minus, if we wrote it this way, these two form a linear pair. So this angle here would be 180 minus angle 1. So if you wrote 180 minus the measure of angle 1 plus 80 plus 150 equals that, well, then you'd be on to something. But as it stands, yeah, didn't make any sense at all. Well, I put this quick little problem up on top here because we have all these examples of triangles right here. And we can use them to figure out which of these is not possible. Well, an acute scalene triangle. Remember, acute just means that all the angles are less than 90. Does that mean that 2 or 3 of the sides have to be equal? Because scalene means that none of the two sides are congruent. So does the fact that all the angles are less than 90 degrees imply that these sides have to be congruent somewhere along the line? No, it doesn't mean anything. So it's totally possible for a scalene triangle to be acute. In fact, lots of them probably are. What about, I'll try B, a triangle with 2 acute exterior angles. That sounds a little shaky. Let's check out the other 2 first and come back. An obtuse isosceles triangle. Is that possible? Oh, I think so. This one isn't, but suppose I drew them a little bit differently. Suppose I expanded these sides out so they went like that. There, pretend both of those sides are equal. Now I've got an angle here that's bigger than 90 degrees. So that's possible for sure. You can do that. An equiangular acute triangle. Well, we can set up a little equation and prove that's possible in about 3 seconds. If all the angles are equal, let's refer to one angle as x. And x plus x equals 380, or 3x, 180, or 3x equals 180, or every single angle equals 60. So it is definitely possible. In fact, it's necessary. So through a process of elimination, this one probably isn't possible. Let's think about why it might not be possible. Well, if these people are right, and one of these definitely isn't possible, and we've eliminated these 3, this must be the right answer, but let's figure out why it's right. Well, let's see here. We've got these 2 exterior angles. Let's try these 2. What the heck? I don't think it really matters much. Is it possible to have two acute exterior angles? Well, you don't even need a proof. Let's just think our way through it. Here's an exterior angle. Let's call this E1 and this is E2. And here's our interior angles, 1, 2, and 3. Now E, we know from our exterior angle theorem right here, that the two opposite angles, the measure of these two opposite angles, add up to the measure of the exterior angle. So the measure of angle 1, measure of angle 2 equals E1. On the other hand, the measure of angle 2 plus the measure of angle 3 equals E2. See, I have room to write that over here, I think. I want two acute exterior angles and see if that's even possible. So I already wrote the important part in a cleaner screen so you can actually keep track of what the heck's going on here. We've got this exterior angle equal to the sum of these two. This exterior angle equal to the sum of these two. And these were totally arbitrary. I could have drawn a line here and gotten this exterior angle equal to this one and this one. It doesn't matter. The point is, the sum of any two exterior angles is going to be greater than 180. How come? Well, if I add these two exterior angles, I get the measure of angle 1 plus the measure of angle 2, and here I get the measure of angle 2 plus the measure of angle 3. That must be greater than 180. Why? Well, because this is non-zero. And the sum of these three is exactly 180. No way around that. Triangle sum theorem. 1, 2, 3. Add these up, you get 180. If you throw something else in there, unless it's 0, you must have something greater than 180. But we arrived at this by just adding these two, which means that the sum of these two, of the measures of these two exterior angles, is greater than 180. So there's no way to break these up such that they are both less than 90 degrees. You can't do it. One of them has to be obtuse. Even if you cut them in half. If one was 90, forget about cutting in half. If one was 90, one would have to be greater than 90 to get a sum greater than 180. So the real question you have to ask yourself is, can these both be less than 90 and add up to 180? Well, no. That just can't happen. So our answer to that multiple choice that was way up here is exactly what we got through the process of elimination. If this were actually on a test, I would just go with the one that didn't get eliminated and move on. But we're not on a test, we've got time, and I wanted to make sure you understood why this turns out to be true. Well, here's one that looks a little screwy, but it's probably not that bad. We need to find x and y. I have a feeling we're going to use our triangle sum theorem somewhere along the line here. But they went and showed us that these are parallel lines, so that's probably going to matter too. Well, what do we have here? Looks like corresponding angles, right? Corresponding angles are congruent, so this one must. So x is 118. Okay. This angle here, we haven't labeled it yet. Why don't I call it Z? I'll use their notation. Draw a little arrow to show that that is this one here. Well, x plus z equals 180. How come? Well, they form a linear pair. X is 118. So if I subtract 118 from each side, I would get that z equals 62. That's this one here. And we know, I guess I can put it down here, that 62 plus y plus this one, which they say is 22 degrees, equals 180. So we got, 62 and 22. So y equals, so we lay out our angle sums, set them equal to 180, do a little algebra, and get that y equals 96. So 22 and 62 is 84, 180 minus 84 is 96. Boom, we're done. So we had that x is 118. We figured that out from the fact that it's a corresponding angle here with the two parallels cut by a transversal. And then we used the properties of linear pair, and then we used our triangle sum theorem. I think just step by step, really. Well, here's one that's likely to bend your brain. This is all done in all variables. There's not a number to be seen anywhere in here. And you're supposed to figure out when these would form a triangle. Well, I think they form triangles when they intersect, right? You got a line here, and a line, and another line. Oh, well, this part in here would be a triangle, wouldn't it? What if two of them were parallel? Well, that's two parallel lines cut by a transversal, but we're not going to end up with a triangle anywhere, unless these two weren't actually parallel. The way I drew them, it's pretty shaky. But pretend these two lines are parallel. It wouldn't work. So, what do you have to know to say that these are all? Well, we have them in slope-intercept form. So what we can say right off the bat is that A, C, and E all have to be unique. None of these two can be equal. If they were equal, that means two lines were parallel. If they don't intersect, then we don't have a triangle, do we? So, they'll form a triangle when A, C, and E are all distinct. No two are equal. What else? Well, we're going to let these variables equal these numbers and see what happens. Okay. In here, they give us some actual numbers for these variables up here. And I went ahead and drew them in. We've got y1 would be x plus 2 based on c equals 1 and d equals 2. Over here we got 4x minus 7 based on e equals 4, f equals minus 7. And what they want is values of a and b so that no triangle is formed by the three equations. Now, they don't say find the values of a and b. These values are not going to be unique. But from a previous problem, we know that if any two of the sides are parallel, we don't have a triangle. So all we have to do is produce equation parallel to this. For instance, suppose our line was x plus 1. That'll be parallel to x plus 2. So we've got a equals 1 and b equals 1. B is extremely arbitrary. If we chose b to be 2, we would have exactly the same line, which definitely would not form a triangle. It seems kind of like cheating to me, but maybe they intended that to be legitimate. It kind of depends on how you look at it. If you want it to be a third distinct line, which still doesn't form a triangle, then b has to be something other than 2, and the slope would still be a slope of 1. Or, alternatively, we could have y2, or y rather, equals 4x plus anything. We just say plus 1, why not? It'll still be parallel, and then it won't form a triangle. So Either of these would work. We have a equals 1, b equals 1, a equals 4, b equals 1. Now here I graphed the two lines, y equals x plus 2 and y equals 4x minus 7. That's this one here. Now lots of lines would form a triangle. Almost anything that, so I say, anything that didn't have the same slope would have the same, would eventually intersect. And for instance, suppose we had a negative slope and it went through the point 3 here. Well, we know enough now. We can do that real quick. Punch it right in. Negative slope, we'll say, how about minus 1? That'd just be minus x, right? And we'll have a, let's try an intercept of 1. That means it should cross right here. Yeah, let's make it 2. It'll be easier to see. Boom. Now, you can see that this crosses. This over here should be like, I think that's a 0.35. Pretty close, that makes sense. If you put a 3 in here, you get y equals 5. If you put a 3 in here, you get 12 minus 7, and that's 5. So up here we get the 0.35. They intersect. And down here, yeah, so we have another intersection. So all three of these equations have common solutions. But suppose we didn't do that. Suppose we drew in one of our lines that we decided was parallel. Boom, there it is. See what happens here? Is we take off to infinity in either direction. These lines are never going to cross. We have a transversal here, but no triangle. Well, and then we could try the other one, 4x plus 1, and that gives us a line parallel to this one, which again will not form a triangle. See? Now this next part, we draw the triangle formed, which would be actually to, what we do is graph these lines, created when you substitute a, or 4/3 in for a, and on down the line. And let's see here. Let's see what we get when we do that. Well, here's what we get. We've got our line y equals minus 1, 4/3 x plus 1/3, and minus 4/3 x plus 41 over 3. And they say classify it according to the sides. Now this side's almost exactly 12 units long, isn't it? Looks like an isosceles triangle to me, but I think what we have to do is a little bit of algebra and make sure. For instance, we'll have to find the distance from this point, it's probably the 0.57, to this point. Looks like 11 minus 1. And from this point to this point. So, in the real world, you can't just click on it and find out what these intersection points are. We have to do a little algebra. So let's do it. Now here I've gotten it started. In order to precisely determine the points of intersection for our triangle, we have to set the two lines, or the equations for the line, equal. This would be roughly 4/3 x plus 1/3. This is the minus 4/3 x plus 41 over 3, and here's the intersection point. How did I get to that? Well, we set these two equal, add 4/3 x to each side and get 8 over 3 times x. Subtract 1/3 from each side, and the 8/3 x is equal to 40 over 3. Multiply through by 3 over 8. The 3's will cancel. You'll get 40 over 8, which is 5. We plug 5 back into either one of these equations. I picked this one, no particular reason. 4 times 5 is 20 over 3, plus 1 over 3 is 21 over 3, which reduces to 7. So that's how we got that point right there. The next two intersection points, they're going to be pretty easy. Because we only have x's in one of the equations. For instance, this one. This is the one with the positive slope, so this is the 4/3. 4/3 x plus 1/3 equals minus 1. This whole line here is just y equals minus 1. So this becomes fairly easy. We got 4/3 x let's subtract 1/3 from each side and get minus 4 over 3. Well, I don't think you need a calculator to see that x equals minus 1. And we already know that y equals minus 1. So this point here is minus 1, minus 1. And this point here is going to be something minus 1, because we know that the y coordinate has to be minus 1 for all of them. So what do we got here? We'll try the intersection of this line. I may have to give myself a little bit of room down here. There we go. This line here with the line y equals minus 1. And that would be, let me separate this stuff here so we don't think that we're doing the same thing. This should be minus 4/3 x plus 41 over 3 equals minus 1. So we set this one up to minus 4/3 x plus 41 over 3 equals minus 1, or minus 3 over 3. Think of it that way. We can subtract 41 over 3 from each side and get 44 over 3. Multiply through by, minus 3 over 4 and get, that's not minus 11. Made a mistake. Hold on. Yes, one more careless mistake. If you're keeping track, this is number 853, and we're not even 1/3 of the way through the class yet. Well, you should pay close attention to what I do, because I make mistakes. And that means this is actually positive 11, which is what I got in the first place. Because I made two mistakes. I ignored the negative sign over here. And ignored it over here. You're supposed to keep track of them. Minus 3/4 on each side. We multiply through by minus 3/4 on each side. And get plus 11 for x. So the point here is 11 comma minus 1. What the heck did we do all this for? Oh, that's right. We want to find the distance from here to here, from here to here, and from here to here. Well, this distance is pretty easy because the y's don't change. So we could take 11 minus a minus 1, square it, and then take the square root. I don't think that's necessary. I think we can just call it 12. It's just on a straight line. In fact, I think when we looked at it here, we figured out that this was probably going to be a length of 12, and turns out we were exactly right. So what we need to do now, since we know that this part here is 12, that's our triangle there. What we have to do is find the distance from this point to this point. That was our top apex to the right hand lower one, and here's the apex to the left. Pardon me, this is the left hand lower one, this is the right hand lower corner. So this is easy, right? And let's see what happens. We'll take -1, -7, and then we square it. I don't know why I did the y's first. That's kind of weird. Probably shouldn't do that. Here's y2 minus y1. And now for the x's, we'll do x1 minus x2. And we want the square root of all that stuff. So what's that? Well, it's -6 squared plus -8 squared. I think it's going to turn out to be 10. But let's check it out. I know that because these are common numbers to use. -6 squared is 36. -8 squared is 48. Take the square root of that. Oh, well, I'm wrong. Good. Because 8 squared is 64, you dope. Jeepers. Oh, gee whiz. I can look at this and tell you right off the bat it's going to be 10, but I can't square 8 and get it right. 36 and 64 is 100, and the square root of 100 is 10. Okay, now let's see what I can do wrong over here. Let's take the distance from this point to this one. We'll do it the same way. We got 11 minus 5 squared plus -1 minus 7 squared. Well, jeepers. 11 minus 5 is 6, and -1 minus 7 is going to be the same as it was up there. So this whole thing is going to turn out to be 10 again. So what have we got? Well, what we got is 10 here, 10 here, and 12 here. We have an isosceles triangle because it said classify the triangle by its sides. These two sides are congruent, and this one isn't. Done. That was kind of a long one. But remember, every time you see something like that, don't get intimidated or frustrated. Just go through it one step at a time. Well, this one's pretty easy. The only thing that could mess you up is the greater than or equal to, or less than or equal to, either way. It's the or equal to part that makes most of these impossible. If one of the angles was 0 degrees, I mean, you've got, think of this as one part of a triangle. If this part drops down to 0, what have you got? You got a straight line. And as I pointed out, I think earlier, in some advanced college math courses, you may analyze a straight line as a degenerate case of a triangle, but no degenerates in this class. The or equal to, nope, no good. Or equal to, no. You remember 180 is just the other side of 0. If I took this and drop it down to 0, okay. Or I can go the other way and put it all the way over here. That's still just a straight line. Get this whole, in other words, this whole angle would turn out to be 180. That's still just a straight line. And we're not going to call straight lines triangles. You can forget all of these ones with the or equal to in it. It has to be greater than 0 and less than 180. Otherwise, you've got a straight line, and we're not going to call those triangles. Now here's one that's going to make use of our main theorem in this section, triangle sum theorem. What is our equation going to be? Well, these two are the same. In fact, they're all a function of the square root of 2x. The same radical is in all of them. So we've got 2 times the square root of 2x. If we were to add these up, plus 5 times the square root of 2x, plus 2 times the square root of 2x. Well, we can just immediately write that as 9 times the square root of 2x. That's just 2 times the square root of 2x plus 5 times the square root plus. And that's 180. That's real easy. So, square root of 2x equals 20. Okay. Now I would just square both sides and write the 2x equals 400. That x equals 200. But we don't have to do that, do we? Because they give us everything in terms of the square root of 2x. It's almost as if this were an x all by itself. Forget about square root of 2x. Suppose we wrote 9x equals 180. And then we'd have that x equals 20, right? Of course that's right. I hope it's right. Yeah, that's right. So we can just substitute 20 in here for the square root of 2x. They didn't ask us to find x. So we just stopped right here. Square root of 2x is 20. Don't make yourself a bunch of extra work when you see this on a test. Recognize that. And this angle is 2 times the square root of 2x. So this angle here, let's put it right up here, is 40. This one is 100, and this one is 40. Does that make sense? Well, 40 and 40 is 80 plus 100 is 180. So, makes sense to me. Find the measure of each angle. Yeah, we just did that. Classify the triangle by its sides. I read that wrong. Classify the triangle by its angles. That makes more sense since everything we found was angles and not sides. So, classifying the triangle by its angles. Well, 2 angles are the same. We could say it's an obtuse triangle. Yep, because one of these is bigger at 90 degrees. Here's our choices up here by angles. They're acute, right, obtuse, or equiangular. So I would classify this as an obtuse triangle. We're all done. Well, remember 4 or 5 years way back at the beginning of this class, we talked about perimeters, and then we never mentioned them again. Well, they're going to come up in this course a lot, and this is only the beginning. So let's remember, we studied perimeter, circumference, and area. Well, remember, perimeter for a triangle with sides A, B, and C is A plus B plus C. I'm sure you remember that. But just in case that squirrel snuck into the class and missed that day, this is what the perimeter is. When I say that squirrel, I'm referring to the one who may have snuck in when we were studying pattern recognition. That's something humans do really well, and squirrels are really bad at it. He could have missed the part where we defined perimeter. So we've got that AB equals x, BC equals 2x minus 4. find two possible values. Well, let's see. Maybe we gotta draw a picture and see what it is we're talking about here. Bad. There's A, there's B, and there's C. So, I'm going to say AB is X. BC is 2X minus 4. And it's isosceles. And the perimeter is 32. We don't know anything about this, do we? Now they told us that it's isosceles. So it's either these two sides are equal, or these two, these two, or these two. Could these two be equal? Well, when would x equal 2x minus 4? Let's see if that's even possible. Pretty easy to find out. See, now that you're experts in algebra, you can just set these things up on your own and find out if something does or doesn't make sense. Unfortunately, this might turn out to actually make sense. Minus x equals minus 4, or x equals 4. Yeah, that would make sense. Darn. On the other hand, maybe we don't have to worry about what's actually possible, but just define things the way we want them to be. For instance, suppose I want this side to be the same as this. Then I can just write an x here. So it is possible for these two to be congruent. Let's find out if that's the best way to work the problem. If I do it this way, I know the perimeter is 32. It's kind of like when we had the angles and they all added up to 180. We don't have anything like that for sides. There is no theorem about what the sides of a triangle have to add up to. They can add up to anything, because you can have any size triangle. It's only the angles that are restricted to add up to 180. So if this is x plus 2x minus 4, so let's call that x plus x is 2x plus 2x minus 4 equals 32. Is that what they said it was? Yeah. So we got 4x minus 4. Oh, it's supposed to be a 28, sorry. And that would imply that x equals 7. Well, suppose we use, they ask us to find two possible values for x. We found one, x equals 7. That'll work. That means these are the two congruent sides. On the other hand, we previously set these two equal and found that x would have to equal 4 for this to be true. Well, that would make this side equal to 28, wouldn't it? Does that make sense? Yeah, I don't see anything wrong with it. It's the way I drew it here is entirely wrong. You would have to be, for x to be 4, it would look something like, wow, it would be like, and then real long along here. Even bigger than that, because this is 4 and this is 4, this has to be 28. It'd be a real long one there. But that's possible. This would just be a really big angle, and these would be really small. That's one way. What else could we do? Well, let's try. Before we decided to set one side equal to x, let's set the other side now equal to 2x minus 4 and see what happens. All this stuff has to add up to 180. So we got 2x plus 2x is 4x plus x is 5. Minus 4 plus minus 4. This is 5x. And that's minus 8. minus 172. As I say, that's 188. Dope. Equals 5x. Add 8 each side and get 188. 188 divided by 5. And there's another possible value for x. We set up the equation, 5x minus 8 equals 180. So we get 37.6, that's 71.2 for these two would be the congruent sides, which of course doesn't look that way. Just didn't happen to draw it that way. Now, if the perimeter is 12, how many possible values are there for x? Well, it seems to me it would be the same, but I could be wrong. Let's work it out and see what actually happens. Let's write the possibilities up here. What did we end up with? We'll end up with 7, 4, and 37.6. I believe that's all the possible values for x, given that it's isosceles. Well, we can start out by remembering that when we set up 2x minus 4 equals x, and you got that x equals 4, that didn't depend on the perimeter. We were just setting these two equal to see if that was even possible. For a perimeter of 12, this would be 4, this would be 4. Oh, and this would be 4. So it's possible. It works just fine. So down here, we also have 4 as one of the possibilities for x. What are we going to do? Well, we could set these two equal, just like we did before, and then we get that 4x minus 4 equals 12, 4x equals 8, or x equals 2. If we set these two sides equal, and say this is 2x minus 4, and this is x, then we're back to the equation we just solved, but with a slightly different perimeter. It would turn out to be 5x minus 8 equals 12. And that's going to be a really strange one, because we've got 5x. Oh. Minus 8 equals 20. Okay. And then we get that x equals 4 again. So we had 2 and 4, but we cross that out. So it looks like we only have 2 possibilities. So it pays to work it out. Off the top of my head, I just said 3. Same as with the original perimeter, but 12 changes things. If this side equals this side, that leads to x equals 4. If 2x minus 4, if these two sides are equal, that leads to x equals 4. It's only when we cross out the 2 and the minus 4 here and set x and x on each side, then we get a separate, distinct value for x. So the answer down here is just 2.